Hello to everyone. I am Roberto Verdecchia of the Universiteit Amsterdam, and I'm going to present a research which was recently published at the Journal of Systems and Software. The research is titled Building and Evaluating a Theory of Architectural Technical Debt in Software-Intensive Systems. And the research was conducted jointly with Philippe Kruchten, Patricia Lago, and Ivano Malavolta. First of all, just to introduce the concept, what is architectural technical debt? We can say that it's the set of architectural design and implementation choices, such as choices regarding the structure of our software systems, the technology used, the languages in place, and so on and so forth. And these choices are made early for expediency, but are preventing further development today. To put it in simpler words, it's the stuff that is very hard to change now while hurting us a lot. The goal of our study was to understand how practitioners conceptualize architectural technical debt. What are the essential concepts and what is the relation between these concepts? In order to achieve this goal, we conducted a mixed method empirical study. In the first part, we conducted a Glaserian-grounded theory, and then we presented the emergent theory to practitioners via focus groups in order to evaluate and refine our findings. This led us to formulate a theory of architectural technical debt, which synthesizes the recurring themes into 9 core categories, 63 concepts, and the relation between these categories. At the core of our theory lie architectural technical debt items. So how do architectural technical debt items manifest themselves in software-intensive systems? Here we see 3 different types, first of one of which is related to a framework, such as, for example, a framework which is not really fitted to fulfill its goal, or technology lock-in, so a framework which becomes deeply embedded in a software system to the point in which it's not changeable anymore, or simply a framework which is not up to date anymore, which in academic literature is referred to as technical lag. Then we have process architectural technical debt, so the items related to the architecting process, such as an old architecture which is not evolved with the continuously changing contexts, such as, for example, minimal viable product, which become the underlying basis, architectural basis of a software-intensive system. And then we have implementation architectural technical debt items, such as a workaround, an architectural workaround that state, or a component which was designed via trial and error fashion. Throughout the paper, we make extensive use of quotes in order to provide further example and support our findings with raw data. The second category we identified are the causes. And here we have external causes and internal causes. In the external causes, we see some prominent causes such as time pressure or simply the passing of time, while in the internal causes, we see lack of knowledge, for example, or human factors leading to introduction of architectural technical debt items, or again, complex business processes, which then translate into a complex architecture. Regarding the consequences of architectural technical debt, here we see in the business-related consequences, again, some prominent examples such as carrying costs, opportunity loss, and higher risk exposure. Then some consequences related to the development of functionality, such as impediments in the development of new functionality that can lead to discarding some of the functionalities, or even to a completely crystallized architecture which can't be changed anymore. Then we have the product development related consequences, such as difficulties in carrying out the parallel work, or even a persistent flaky behavior of an architecture. Regarding the symptoms, rather than being consequences per se, symptoms can point to the presence of architectural technical debt item, especially if symptoms co-occur. And here we see issue-related symptoms, such as, for example, recurrent customer issues or recurrent patches or a high number of defects. Then resources-related symptoms, such as the need of senior or specialized staff. Performance-related symptoms, and development-related symptoms, such as developers simply saying, I would rather not touch that component. Regarding the management strategies, so how is architectural technical debt managed in practice? Here we see three different types: active management types, so to fix architectural technical debt before it becomes a problem; reactive management strategies, so fixing it when issues start to emerge, such as, for example, opportunistic patching or major refactoring, or even completely writing the product from scratch. And then finally, passive management strategies, which is neglect, so simply closing an eye on the architectural technical debt presence and continuing development activities as nothing is there. People, of course, play a key role in the development of software systems, so people is also a category which emerged in our theory. And here we see, for example, how architectural technical debt can lead to a lower morale, how the seniority and skill set of people can lead to the introduction and resolution of architectural technical debt items, and the personal drive that can lead people to champion the refactoring or the maintenance of a certain architectural technical debt item. Then we have communication, so how people communicate concepts related to architectural technical debt. And this can range from the exposition of architectural technical debt items, the impediments which arise when talking about architectural technical debt, or even the blame. So developers who blame someone who is potentially the one who introduced an architectural technical debt item or didn't manage it properly. Finally, we have prioritization strategies that in our theory do not follow an established methodology, but rather rely on the gut feeling of software developers. To conclude, in this paper we present a theory of architectural technical debt, and it describes and connects the different architectural technical debt items, category and concepts that we identified as related to this phenomenon. And we, of course, this is a grounded theory study, so it constitutes a mid-range substantial theory. So we more than welcome extension and refinement of our findings. The theory, we hope, can support practitioners in understanding the architectural technical debt they experience. We also got contacted by some developers to ask further questions or to confirm our results. And the theory can also be used as a starting point for researchers interested in architectural technical debt, such as, for example, we are interested in architectural technical debt identification, and we believe the symptoms which are presented in this theory can be used in order to quantitatively identify the architectural technical debt which is present in a software-intensive system. This concludes my presentation. I'd like to thank you all for your attention, and I'm always open to any question you may have. Take care.